Hi there, I'm Mike Glass with Orion Technical Solutions, and today I'm going to talk a little bit about syncing and sourcing I/O, inputs and outputs. I'm going to talk about some of the common misconceptions, mistakes that happen, as well as going over some tips for troubleshooting and making sense of faults and failures that are often misunderstood or misdiagnosed with syncing and sourcing I/O. Okay, so the first thing I'm going to talk about is a sourcing sensor with a syncing input card. The figure shown here is a typical input arrangement. It's got like I say, a sourcing sensor and a syncing input card. This is the most common approach you would see on your PLC or DCS digital inputs, but it is not always this way, and that's what leads to problems. Notice how the positive side of the loop supply voltage goes through the sensor to get to the actual input of the card. And then inside the card, through little photo transistors and other sensing, circuitry and so forth, it syncs to common. The the way that we like to say this is the sensor feeds the source voltage when it's closed to the input channel, and the input channel inside this card is where it syncs to common. Okay, so now we're going to talk about one that's a little different. We're going to talk about a syncing sensor with a sourcing input card. So basically, what's going to happen here, we have a syncing sensor. Notice how the sensor is connected to the common side of the power supply, and how the PLC inside the PLC card is fed to the positive side of the power supply. So, or the source side, we'll say. So in this particular arrangement, power or source is applied to the card. So the card is actually sourcing, but the device is how it syncs to common. So basically, whichever side of the power supply that the thing is on is how you can determine whether it's syncing and sourcing. And basically, you're always going to need a syncing thing and a sourcing thing in the loop, because you're always going to need a positive and a negative side for that to function properly. And we'll talk in a minute about how this gets confusing to people when they troubleshoot if they're not thinking through and really thinking about the equivalent circuitry and so forth. Okay, so the biggest problem that happens when people are testing I/O circuits is due to not thinking about or even being aware of the actual circuit arrangement, or making assumptions based on what they saw typically, right? Most people, not most, a lot of people think if the thing is on, you'll have 24 volts, but that all depends on where your meter is where you're measuring in reference to, and on the circuit itself. So basically, making that assumption that on a 24 volt system, saying 24 volts means on, is absolutely incorrect. That's not always true. Sometimes zero is on, and it depends where you measure. And that also we'll talk about. So in this diagram here, if the multimeter leads are placed directly across the sensor, so basically right across here, it would show source voltage when the switch is open, assuming it's a hard contact switch like a float switch or a physical toggle switch or something. But if you place the negative lead on the negative side of the power supply and the positive lead at the top side of that switch, in this case, you're not going to get 24 volts when that switch is open. You're going to get zero, because this is closer. There's some fairly low impedance in reference to an open contact circuitry in between here, and that's going to make it seem like this is at your common point. And so if you're measuring from here to here, you're essentially measuring just the voltage drop inside the card, which is minimal. Um, So that can really cause confusion. Now, if you were to close the switch, all of a sudden you're applying 24 volts up to channel 1. So if you measured in reference to your, if your negative lead is on the negative side of the power supply and you're measuring your your red lead, your positive lead is on the channel 1 input, when the switch is closed or on, you would see 24 volts. But if you just measure across the switch, when you close the switch, you get 0 volts, which makes sense. You should always get 0 volts across a closed contact. Okay, so to kind of reiterate some of this and talking about the voltage measurements, um, if we use this less common setup, we have the negative or the negative side, the common or the neutral, we'll say, of the power source is connected to the switch, but the positive side is connected to the actual input card. In this situation, it gets really interesting. If we place the negative multimeter lead on the negative side of the power supply and the positive lead on the top side or the channel 1 input, when the switch is closed, we're just going to see 0 volts because really we're just measuring across the switch. We're measuring from here to here. When the switch is open, we will basically measure 24 volts or roughly the source voltage, assuming this is a hard contact type sensor. Um, that is one that leads people to confusion. It looks a little strange because you're not applying power to the sensor or the switch. It's allowing the common return. It's just closing that. It'd be like putting a light switch on the neutral return of your house. Uh, and we actually do have this. This is a fairly common thing in the industrial world for various reasons. We often do end up with digital input cards that are sourcing cards that use a syncing sensor. So you definitely have to kind of be aware of this and think about it. To look at the card, it'll say sourcing or syncing on the top of the card typically. And based on that, you need to think about what is the equivalent circuit in your mind so that when you're troubleshooting, you're visualizing the schematic, if you will. Okay, so just when you thought it can't get any weirder, um, if this switch instead of a switch like a float switch, hard contact, if that sensor is something like a solid state device, let's say a proximity switch, a photo eye, or other types of basically electronic type sensors that have solid state electronics inside them, it gets a little weirder because their impedance is not like infinite and zero like a typical contact would be on a float switch or pressure switch or something like that. Their impedance can be, can vary between, let's say, 50, 100 ohms, 1,000 ohms when it's on, and maybe 10,000, maybe 20,000, maybe more when it's off. Likewise, there's an impedance inside the card, and that can vary. That can vary. It could be maybe down into, hundreds of ohms, more likely into the kilo ohms, maybe 5K, something like that. 10K could be much more. So you got a balance of these two impedances, and that in 24 volts, well, it becomes kind of a voltage divider. Some of the voltage will be dropped here, some of the volts will be dropped here, and it depends on what the impedance of the sensor is at the time. So if it varies between, let's say, 1,000 ohms and so let's say 20,000 ohms, and then this one over here is typically 10,000 ohms, you're going to get a lot of interesting readings. It's not going to be, in this case, 0 and 24 volts. You might be getting 2 volts, 5 volts in one condition, and maybe 22 volts or 23 volts in the other condition. So basically, you really to really know what you're doing on this, you're probably going to have to go look at the cards you have and know what is the impedance of this card. What's the standard impedance of your particular digital input or digital output card? And then you're going to have to kind of know what is the on and off impedance of the sensors that you're measuring, because that ratio is what's going to determine the voltage basically. And we'll analyze some of that in the next slides. Okay, so the voltage measurements, as far as making sense of some of the more confusing options or arrangements. In this case, we've got a syncing sensor and a sourcing card. That's kind of the less typical and the more confusing option that we just kind of discussed. If you place the negative multimeter lead on the negative side of the power supply, and you place the positive lead at the channel 1 input, when the sensor is on, i.e. closed, you'd read close to 0 volts. With a switch, you'd read 0. With an actual hard contact, you'd read 0. But with a solid state device, it may not be 0. It may be a fraction of a volt, maybe a volt or two, or possibly even more. But if you perform the same measurement with the sensor off, you're going to see close to source voltage. So you may see roughly 23, 24, close to 24, maybe a little bit less. Again, it depends on the ratio of the impedance of the input card and the sensor in that state. And of course, it matters where you put the leads. If you put the lead just between the card reference, which in this case is at the plus 24 volt point, well, then you're going to get different circumstances. So it's kind of dependent upon where you're measuring, and you have to be able to think about these equivalent schematics when you're doing those measurements. So that oddity or that it's not consistent. Depends on the type of card. And that's where a lot of the confusion comes from. People get used to just doing a measurement a certain way, and they don't think about how the actual circuit's hooked up. And of course, when they get results, they're misleading. And so they think they have a problem in one place, when in reality, that indication tells them the opposite. It's saying, hey, this is a good sensor, or this is on, or this is off, when they're thinking the opposite. Okay, so let's talk about digital outputs. In this case, I have a syncing load with a sourcing output card. This is the most common arrangement for digital outputs. But again, it's not always the arrangement. In this case, we apply power to the card. There's something in here, a little optical isolator or phototransistor, something that turns on and allows that 24 volts to be applied to channel 1 or channel 2 or whatever. And that applies the source voltage to the solenoid. Well, the solenoid then syncs it to the common. So that is, again, that sync source concept. Once you start thinking about one side's plus, one side's minus, the supply is the source. The common or the neutral, if you're dealing with AC, would be the sink. And so it becomes pretty easy to figure out which one are you dealing with, the sourcing or sinking, etc. Okay, so this time I have a sourcing load with a sinking output card. So notice how the source, the positive side of this power supply, is applied to the solenoid. That solenoid's hot all the time. That's not a great idea in some situations for a solenoid, but again, it does happen. There are cases where this is used. So you have 24 volts applied here, and for that to turn on, it has to sync it through the card. So the card is controlling the return, if you will, or the common. So there's, again, a little photo transistor or something in here that turns on and allows the common path. Without that, you just have 24 volts out here, but you don't have current flow because it doesn't complete the circuit. So this one is really tricky because it behaves somewhat opposite of the typical arrangement as far as voltage measurements and so forth. And again, You have to understand Ohm's law. You have to be able to make sense. You don't have to be like a rocket scientist to be able to do Thevenizing and Nortonizing circuits and simultaneous equations and Ohm's law, a lot of the other stuff they teach you in trade school. It's all great stuff, but the reality is if you just understand the simple battery circuit with a lamp, you got it. But a lot of times people went to that trade school 2 years or even 4, and somehow they've forgotten all that, and they're out there troubleshooting and they're not thinking about this stuff. So that happens, and that's one of the reasons in our courses we kind of do that review, because without that, you're really, it's like not having a multimeter, because if you can't think through the circuit, you may as well not have that cool looking little, $1,000 yellow tool in your pocket. Okay, so let's analyze this sourcing load with a sinking output card. If you place the negative lead on the negative side of the power supply and place the positive lead at the channel 1 output terminal, or i.e. the top of the solenoid, when the channel 1 output's energized, you're actually going to see a low voltage. So when the output's on, it's actually making it 0 because it's connecting this negative, if you will, or this common point to the channel 1 output, and it's completing the current path. That's a little backwards from what a lot of people think. They see the little red status light on in the PLC and they think, oh, well, it should be giving me, in this case, 24 volts. And they don't see that, and then they go on a wild goose chase. If you're measuring those same points from here to here, when the output is de-energized, well, in that case, you're basically going to measure roughly 24 volts in this case, or source voltage, depending on the ratio of the impedance of this device compared to this. And it isn't necessarily going to be exactly 24 volts like it would be if, this was like when we're looking at inputs and hard contacts and all that. It's a ratio of the impedance of these two devices. If you happen to have a high impedance solid state device out here instead of a solenoid, right? Solenoids typically have fairly low impedance, a few hundred ohms or something like that. But if you had something like, say, a VFD or maybe a smart intelligence starter, an E3 Plus, or maybe a smart drive, something like that, or even an LED indicator that has pretty high impedance. The voltage may be divvied up quite interestingly. You may be surprised at, when you think you get 24, you might get 20, you might get 18. You can get some really crazy numbers if that ratio is close. If it's not like a 50-to-1 ratio, you can get some interesting readings. So again, you have to understand what sink and source means, and you kind of need to be able to know what are the impedance typical values for your cards and for the devices when you start seeing those strange numbers. And just when you thought it was safe to go back in the water, there's more. Some of these digital cards come with diagnostic capabilities in various forms. For example, a lot of your digital input cards on a lot of PLC systems and in critical applications, gas and oil, energy, etc., actually come with that diagnostic tracer feature. So they're basically pumping out a small amount of current through either the input, and of course this is an output, through, say, an input, and they're making sure that circuit continuity is good. So if the wiring to that switch were to come disconnected, it would actually know, and it would say, hey, I have a IO fault, and it can actually easily, with decent programming, can communicate that to the operators. It often isn't utilized, which is tragic, waste of potential, but it could and should be. Then when you have a wire that came disconnected from a start button, let's say, for some system, the operator knows, calls the instrument shop or the electrical shop, says, hey, we got a problem out here. They run out, check it, fix it before it ever becomes a startup issue. That's a great functionality, but that little bit of tracer current on a digital input card, diagnostic digital input card, is going to cause some voltage across the load. So it might be a couple volts. It's typically a small voltage, but it is a voltage. And interestingly, if you have like LED indicators, everybody's going to LEDs and this and that. Well, the problem with LED indicators are very high impedance, and guess what? That that LED will light up just a little bit. You may or may not notice it. When the lights go out, you may go, "Why is that light glowing dimly?" I've even seen it where people are confused. They think it's on when it's not. Um, so that is a issue. And of course, the voltages get confusing when you're troubleshooting and so forth. And the same thing, likewise, if you're feeding those signals to things like VFDs and intelligence starters, smart buckets, and other, intelligent devices that are typically solid state and so forth, you can get some really interesting problems where under certain conditions it thinks it has a start signal or a run command. So there's a lot going on there. And again, it goes into all of this same stuff with understanding the impedance of this little simple loop. It's just impedance here, there's some impedance here, and then there's a power source. If you can if you can think that way, you can solve a lot of this stuff and figure it out. So if you understand Ohm's law and you can find the equivalent circuits and get those specs, it's not going to be a problem. It's usually pretty easy to solve. Okay, talk a little bit about some tips and tricks if you deal with troubleshooting PLC or DCS cards, or even single loop controllers for that matter. Um, Good thing to do: look at your PLC and DCS systems and look for digital I/O cards that have either a syncing output card or a sourcing input card. Those are the ones that are gonna cause the most confusion. If you do have them, note which ones they are. Make a list, whatever. Make a list for the whole shop, ideally, right? And share that info. Um, Basically, go through and do some sample measurements on a healthy system on the on and off state for each typical type of sensor that you have. You don't usually have 1,000 different types of sensors. You may have 5 or 6. You may have one. But check if it's a certain kind of photo eye. It's a banner, reflective photo eye, whatever, certain model. Maybe you have 2 different types. Check that on each one and record that. Say, this is what this does when it's on, this is what it does when it's off. And it might be close to 24, it might be close to 0. If it's AC, it might be 0 and 120, or it might be not quite there. But record that, take a note of it, and then sit down and make sense of what you just observed. Like, don't just record it and count on that. That's the worst thing you could do. Sit down and think, why did I get 22 volts in the on state, and why did I get 2 volts in the off state? Once you've thought through that, put those notes on there. Say, this happened because, and then share it with everyone. And I mean, you could even post that inside the enclosure, right inside the panel. This is how this is going to work. Super handy. You forget, you just look at the inside the panel. Oh yeah, on these we should get this, and no, that's why. Got it. The other tip: don't become habitual about how you do measurements. I've always found the guys and gals that struggle the most, it's because they're just doing the steps. Well, this is what I did before, and they're not thinking. The best techs, the good techs, are always thinking about what they're doing. You don't just automatically place the lead here and place the lead there and assume that this voltage means this, and the other voltage means something else. You got to think through the circuit. I think I've said that a couple times in this video, but it is absolutely an issue. Almost every time there's confusion, that's what happens. Every time you're doing a measurement, you should be thinking about that circuit, and you should know what you're going to expect before you do the measurement. When I would assess techs, that's one of the things I'd put a fault in or something and watch them troubleshoot. And they'd go to measure something, and right about the time they put the leads on, I'd say, "What do you expect to see?" If I'd stop them and say, "Explain to me what you're looking for, and what do you expect?" And surprisingly, more than half the time they had no idea. They're just looking at a number, and they're like, "Well, I don't know. I'll figure it out when I see it." Well, that's backwards thinking. That's gonna lead you down the wrong rabbit hole. Think about what you expect, then look at it, and then if you don't see what you expect, think about why. And again, I think the key word here is slowing down and actually thinking, and not just trying to quickly do a measurement and like it's going to beep or buzz or say here's the fault. It won't. It's counting on the human to sort of figure that out. So that's our part. So because these problems, because these issues and other ones like them, they cause so many problems in the field. We tend to cover this and other issues like it pretty extensively in our labs and in our courses. Basically, um, we want to make sure that students really understand the issues that we know cause problems in the field. They cause the troubleshooting to go on for days. That cause the circular troubleshooting where assumptions cause it to go the wrong direction, etc. In doing literally decades of training and assessments for instrument, electrical controls, automation techs, and in all kinds of industries, we have a pretty good picture of what's causing the weaknesses and the problems and so forth, and really what's costing money and what's endangering people. What's causing the risk factors to go up. And we found ways to teach those concepts and solve those problems. So we really try to build that into our courses. One of the things that I see a lot is, to be honest, course outlines that are bullet points that are just meant to sell to the, I guess I'd call it the uninformed manager, who knows the keywords but does not know what they mean, who doesn't know why or how any of this knowledge matters. Often those managers don't fully respect their best techs. They don't fully understand what good looks like, even sadly. Um, our course outlines are built with a purpose. They're built to improve results, and it hurts us a little bit that we're not creating the bullet points. Um, but the folks that actually attend our training, and the managers that really understand something about it, they see that. They see the real value, right? The actual, you can't teach everything about PLCs and controllers and process control and instrumentation in 3 days. If somebody tells you they can, they're lying. There's a reason people go to school for 2 to 4 years just to start in these fields. Um, but we really try hard to build each of our courses to accomplish the course objectives. I mean, that's literally what guides the development of the courses. And uh, we that is our number one goal, is to actually produce the results, not just to sell the course or fill the seats. And you'll see that when you take our courses. And this is one of the topics among many others that we spend some time on, and we actually make sure people get to practice and experience and understand. So hopefully you found this helpful, and feel free to reach out to me, Mike Glass, with comments, inputs. If I missed anything on here that I overlooked or double spoke on or anything like that. Thank you.